I just want to start with a couple of things. So Textbook was easy to find,
Yeah. Nice.
and quiz works.
It works.
Yeah.
Unlimited tries,
Yeah, tries.
5-minute cooldown.
5-minute cooldown.
Alright. So as I mentioned before, the first chapter is really just the introduction to the course. And we covered this part and this part. But you guys read about the layers of abstraction and the components of activity, yes.
Yes.
And then performance is really chapter 2. So you will start reading this or try it, but you could have already. Okay. So there are a few key ideas in pure architecture, and one of the biggest ones is using abstractions to simplify your design process. And another one is that we want to make the common case fast. And then we can increase our performance through these 3 techniques: parallelism, pipelining, and prediction. These 3 ideas we are going to get into towards the middle and end of the course. But these 2 we will cover very quickly. And then at the very end of the course, we'll talk more about the hierarchy of memories. But that is mentioned early on as well. But we'll get into the details later. So abstraction. So this is used by both computer architects and programmers. So anyone want to tell me where it's used by programmers, since that's what most of you are, right?
They just, for example, like we give a general idea of what a function does without having to go into like the low level details. Or like a program, for example.
So are you talking about like before you even start coding?
No, it's like after the project's done, for example, like a program. And then like hardware, it's not that.
So you're talking about like documentation? Like if you're writing a package?
No, something like that, but it's more along the lines of say like if we're trying to sell like a product and to like whoever our client is, we give them like a brief idea of what this program does without having to give like the lower level details.
I could see that as, so like trying to talk to the customer in a way that they understand. Yeah.
Abstract classes that have defined method names but without any actual code in it.
So you have like kind of a super class that your other classes implement. Yes.
Just using the programming language itself.
Yeah.
A layer of abstraction.
Yeah, so the programming language itself is a layer of abstraction. Why do we like this?
Because we don't want to write in binary.
Well, there's another layer of abstraction in between the programming
Assembly
language and the binary, but yes, you don't want to write in assembly language, right? Your programs would be thousands of lines long. And it would be impossible, pretty much, in a reasonable amount of time to understand what one function does. Okay. So we have it for simplicity, right? But what's another reason that we like this abstraction?
It keeps things simple for us, so we don't have to worry about all the.
Yeah, so that goes back to simplicity. What's another reason?
It increases the programmer's productivity.
So again, simplicity. Okay. It's another reason.
Portability.
Yes, portability. So what do you mean by portability?
I guess because different machines are specific in architecture.
Mhm.
So when it comes to assembly, I guess it's much more specific.
Yes.
But the compilers are designed, I guess, so that it's more portable in different systems and machines, you compile it with the same language.
Yeah.
Um,
So long as the compiler supports these different machines, or what we'll talk about later is the instruction set architectures. We can have the same high-level programming code be compiled for different CPUs. So like if you have your code in Java and you're going to compile it for x86 versus for ARM, right? You can use the same high-level code. You don't have to rewrite it. So we already talked about these different levels of representation a little bit. We'll go into more details. And this was a key point that we discussed. So lower level details are hidden to offer a simpler model at those higher levels, and it helps you be more productive, like you mentioned. So the way that it's helping you is because we have this enormous complexity at the lower levels that we don't want to really have to worry about when we're programming. So here are the different levels, right? So this is what you guys are used to looking at for the most part, and what you would be working at when you go into industry, right? High level programming language. But what's another level above this that you might be working with? We not quite data structures. We've kind of mentioned this already.
Pseudocode.
Not pseudocode. Pseudocode's kind of like the same level of abstraction.
User
Yeah,
interface.
so object-oriented programming is a good one. But then also, if you're just using packages, like from what is the word that I'm looking for? Someone should announce it.
Like a library.
Yeah, libraries,
API.
APIs. So if you're like trying to adapt something to work with, say, Twitter API, which is no longer a thing, right? Or Reddit, also no longer a thing, but these things still exist. So high-level programming languages. The compiler then translates them and tries to optimize them for different assembly languages. And then once you have the assembly language, you can use the assembler to translate it into the binary machine code that the CPUs can understand, right? And each one of these 32-bit instructions, 32-bit strings is one instruction. All right. So further into this abstraction idea, we have different layers, like from the hardware to the software, and then application software. This is application software. Above it would be your APIs. Okay. So here we have your programs that are the application software, right? Written in these high level languages. So like Microsoft Word, email, games. And then there's system software that are written and they're part of the operating system. So they're handling your inputs and outputs and managing the memory, how much memory that each application gets, what section of memory that they get, how much CPU time they even get, and switching which program is on which core of the CPU at a given time. And then there's the hardware abstractions. But these are more of just like what is the hardware comprised of. So you have your CPU, you have memory, and then you have input output devices, like your mouse, keyboard, display. And basically your system software or your operating system is the abstraction between hardware and software. Here it is again. That's a little bit more detail. So this is the key divide in terms of abstraction layers between hardware and software, the instruction set architecture. So this is your set of assembly language commands that is understood by the CPU under. And then here's your microarchitecture that implements that ISA, right? And then below that, you have the digital logic design of that microarchitecture. So in this course, we're going to mainly be talking about the microarchitecture part, as well as the instruction set architecture part. So we're right on the line of the hardware and software divide. Okay. So you have done some digital logic design in 231, right? You learned about the AND gates. You learned about AMAPs, things like that, two-level logic implementation. So we will talk a bit about those, but we're mostly going to be talking about those digital logic blocks as like this black box. And we just know what the function is. And then below the circuit design is the actual layout on the real chain. So this is more of a graduate level course to get to this detail. All right, so first checkpoint. So why is abstraction important in designing a system? And here are your options, and your code for today is 963. So again, do this on your own first. Just RRIS. And 963.
Yeah, 960.
So
TV.com.
change student ID.
Or EV.com.
You know, their ID.
I think that's.
I think that's it. Maybe I can change it.
Yeah, and then just.
Yeah, just more. It's really, it's the 963.
Let's see.
What was the code again?
963.
Yeah, 963.
Justin Moore.
Yeah, I think most of you are done answering this on your own. Don't worry if you have not finished. There is still your instruction time because we're not quite at the threshold that I like to be at to move on without discussing. So do talk to the people around you, see if they can convince or you can convince them to change your answer.
Yeah.
You know what?
And then you have the abstraction higher to be deeper like this is a different process and it's all the same which I allow it to write as we do. And they try to
Oh, yes, like the whole.
So that's why I also play with Apple.
Oh,
So that's I think that's what.
When in doubt.
Yeah, right. So what we think concern is why not?
You know,
Our programs like actually, sometimes the assembly code to generate, sometimes not. So, and I don't know, like,
I wasn't sure.
I was just the idea that's what portability. Yeah. And, yeah, you know what? You take it from that context, you know what?
I do agree that this first part.
Yeah.
But it also could have to be the veterinary.
The context.
I get it.
But I have that happened. Because I'm not sure
Here's our discussion dying down on the topic.
You see the assembly code.
So you guys did more towards the correct answer. Show you the results here. So we were at probably 68, 70%. And now you've moved from E, it was mostly D, and moving towards E, which is correct. So we all are clear on A, right? And B goes along with A, right? Because it's more simple. We're able to be more productive, which reduces programming time. We don't have to code in binary or assembly. We no longer have punch cards. In case you didn't know that the way that you used to program before was with actual physical punch cards. If you wanted it to be a 1, you had to punch a hole in the cards. So we don't have to do that anymore. So that increases our productivity, which reduces our programming time. So the one that we are or were on the fence about was enabling targeting different hardware more easily. So this goes back to what we talked about over here. I forget who exactly it was, but we talked about how with the same programming language, we can just change the compiler settings to target a different architecture, right? So because we can do that, you can just write your code once in the programming language and then be able to hit different markets. Like you can compile it for x86, which would be most consumer grade CPUs, because that's what Intel and AMD are using, right? And then you could also target ARM, which is now on Mac, as well as most mobile devices, right? So like your phone most likely is implementing ARM, right? And again, this also goes with B, right? Because now I don't have to rewrite my code multiple different times to target different hardware platforms. All right. So as I mentioned before, we in computer architecture, are going to be right on that line of the hardware-software divide in the abstraction layers. So we are going to be talking a lot about instruction set architectures, as well as the machine organizations or the implementation of those instruction set architectures. But we're mostly going to be talking about a subset of the MIPS ISA.
Quick question. Earlier you said ARM was Mac and mobile. What was the first one again?
x86. So x86 was developed by Intel and AMD licenses it.
Developed by AMD.
Slightly unrelated, I was just wondering, what is the kernel exactly? And
That's operating system.
that was just something, a different.
Yeah, it's just a part of the operating system lowest level. So part of the kernel might be the scheduler. So what program gets to be running on this core of the CPU? And when does it need to be swapped out? What is the priority? Those things. You would learn more about that in operating systems. Right. So instruction set architecture, lowest level of software interfacing with that hardware. So it is very important that you get this part of the equation correct, because you do not want to have to change your instruction set architecture. Because if you change your instruction set architecture, now suddenly all of the programs that you have previously compiled and run on your old CPUs will not run on your new CPUs. So this is a mistake that we are seeing come more to a head lately with x86, right? So Apple's M1, M2 chips, they're much more efficient than what Intel and AMD are talking about, right? It's all because of how, going back to this slide, begin. Make the common case fast. So it's easy to make the common case fast if your ISA is simpler. So x86 is a very complex ISA. And actually the way that Intel and AMD are still kind of close to efficiency with ARM is that they use the first few stages of their CPU design to translate the x86 instruction into multiple simpler instructions. All right, so the instruction set architecture is this set of assembly commands, right? So like add these two registers together, load this data from memory into this register at this address, and then stores the opposite. Take the data from this register and write it to memory at this address. And we also define the different components of the CPU. So what are the different data types? What are the amount of registers? How large are these registers? And different addressing modes. Can I only access memory by register? Or can I have a register plus some intermediate offset? Things like that. And your key decisions here are, what are your operations? How many of them are you going to need? And what are your operands? How many operands should your instructions have? Are they registers? Are they memory locations? Are they floating points? Are they integer? Things like that. And then based on these things, you need to figure out what is my simplest instruction format? How can I have as few instruction types as possible? And what we find most of the time is we want them to be the same size. So here again, examples, ARM, x86, and what we're going to talk about, MIPS. So IBM has their own, right? They actually have multiple, 360. PowerPC is also from IBM. And then Dell SPE, also IBM. And then below the ISA is the implementation of that ISA. So you would take the ISA, it tells you how many registers you're expecting, what needs to be implemented in the ALU. So this is the arithmetic logic units. Do I need to implement add? Do I need to implement subtract? Bitwise and, things like that. Do I need a shifter? This could also just be in the ALU, but you could also need separate ones. And then what are the other logic units that I need? Do I need a floating points units to do floating points operations? So the CPU architecture is going to figure out how these units are interconnected, how the data is going to flow through it, and how to control that flow. And again, your examples. So Intel's, they have their old Pentium chip line, and then they have their core line that goes up to i9s now. And then we have AMD Ryzen nowadays. And on the server side, Intel has Xenon and AMD has EPYC. So your microarchitecture is going to implement usually one specific ISA. So Intel, AMD, like I mentioned, x86. And then this obscure chip, I'm not sure where it's from, implements ARM. But you can also Raspberry Pi, that's implementing ARM. So this is kind of the basic idea of your computer, and it's going to be the same across the 3 different classes that we talked about last time. You're going to have this inputs and outputs where you can write and read data. And that's also where your program is going to live, along with the data. And then your processor has these 2 different components to it. The control part, so how the data is going to flow through, and then also the data path. And what the processor needs to do in order to do any operation is first read the data and also read the instructions from memory, get that into the data path, perform that instruction based on what the control interprets from the instruction itself. And then if you need to write back to memory, you write back to memory. Okay. So there are many different kinds of inputs and outputs. You have your display, like this one, okay? Your keyboard, your mouse, and then like we talked about in the post-PC era, we also have touch screens. And within that touch screen, we have a keyboard. You could have a mouse. There are accessibility applications. And then our storage devices are going to usually be a hard disk for lots of storage. We don't use CDs and DVDs anymore. And then we have flash, which is also becoming much more common than hard disks because they're becoming cheaper to manufacture and they're getting better density. Okay? And then to communicate with other computers, we have network, which is also input output. Okay? Okay. So we have 2 different types of memory. Non-volatile. So what does this mean?
It's when you power off, the memory disappears. Or no, that's volatile. Non-volatile means when you power off, that memory stays.
It's for forever.
I think it depends. I think for 5.
Reasonably forever.
Yeah,
It's something for most non-volatile standards, it's something like 1 million years that is expected to stay there.
Forever for me.
Yes, forever for you, unless you destroy it, right? And then volatile is the opposite, like you mentioned, right? As pretty, not right away, but within seconds. Once you turn off the power and stops providing that power to the device, the data is going to discharge. Okay. So one thing that we usually find as the trend is non-volatile is very large, very high capacity, and cheap. And then volatile memory is very small, very low capacity, low density, and very expensive. So that's where the memory hierarchy comes in. Okay? You're going to have volatile memory at the top where it needs to be fast, and non-volatile memory at the bottom where it doesn't really matter how slow it is, as long as it's reasonably fast. But what's more important is, can it hold my programs and my data without needing constant power? So here's your memory hierarchy. So all the way to main memory, registers L1 cache, L2 cache, and main memory, those are all volatile memory. Flash memory all the way to magnetic tapes are all non-volatile memory. So we still see magnetic disks, right? So those are your HDDs. We see optical disk less, right? Do we still see magnetic tapes?
like for one really long-term storage, I know some companies do use it
Uh-huh.
as like a backup offsite.
Yeah. What kind of storage do you think makes sense? Like, what do you want long term, but also makes sense on a magnetic tape where you have to physically unroll it if you wanted to read it?
Like what kind of data?
Like video, like movies.
Video, audio, streaming data.
Where does an SSD fall under the hierarchy?
It's flash.
It's Flash?
Yeah.
Okay.
Other question? So usually it's surprising to many students that magnetic tape still exists. All right, so inside the processor, we already talked about this. We have the data path, right? We have control. And then we also have this cache for memory. So this is the non-volatile memory that is going to be small but fast so that it can keep up with the much faster data path. And we use it as this buffer for our data and our instructions. So this is what our registers are going to be named from. And also where we're going to store the instructions. All right, so here's the next checkpoint. So again, answer on your own first. mostly done answering this individually. So you guys are split 50-50. So we don't like, we're contentious on which one? A. So talk about A with people around you. Does it reduce this?
I think it'd be.
Well, I think it's definitely like instead of having the whole way to access. At first I was like, I wish there was a day. I think the end. Oh, really? All of the conflicts like, now we just all through, like, data you can access often. But yeah, it's like, a bigger so I guess that's how I idea reducing those. Right. That makes sense. Again, if you think about it.
That's where I was.
That's where I was sitting in with it too, so there is this.
Yeah.
Hierarchy.
Yeah.
If you had magnetic tape, it would be very, I would think it would be complex access.
Ideally, like, if everything was working.
I was more saying yes for A and B,
Too expensive.
and then C on the. That was the only one that had more.
So I think A,
I'll turn to,
like, for.
what about you two? What are you thinking? Maybe, and then the complexity of accessing data, is there a reason why you don't think it's a factor with the memory hierarchy?
I mean,
makes sense.
Yeah.
like it could be and it couldn't be,
Hmm.
like, depending on how you look at
We were talking about like.
That if you were
access
convinced to change your answer, do change your answer.
And again, that could also be spreading the situation as well.
So we have moved. So do we have any advocates that it does reduce this?
With like reducing the complexity of
Yes.
accessing data. Isn't that with like the speed of which, so the whole hierarchy thing, you have the top of the line being a faster accessing to the memory, and like the magnetic tapes is like the slowest of accessing it?
I must
So-
agree.
So you're saying it reduces the complexity because you have different speeds?
Correct.
Okay, so any advocates for that it does not reduce complexity?
We all chose E.
Now, there are people that should.
I mean, this is like, there was an example of this with NVIDIA recently, because they reduced their bus width on their memory. But they were talking about their cache, and you probably know, like, the concept of like a cache miss, like, so like if there's multiple levels of cache, and then you have to go to the RAM after that, like, for me, that's more complex, because it's like, you gotta search the level 1 cache, is it there? No. Search the level 2 cache, is it there? No.
Yes.
And then you go to the RAM.
So by having multiple different devices where we're storing the memory, it kind of makes it more complex to access data. So if we had one big place of data, it would be much simpler, right? Than having multiple different levels. But we have the multiple different levels to increase our speed, like you mentioned. So the correct answer is D here. D and C.
I was 2/3 right.
Yes, yes.
Can you actually elaborate on like how it reduces processor?
Hard to understand.
So
To understand.
so we have a question about C. Why does this reduce processor area? So on our processor, we have the registers, and also we need to store instructions. And say that was our only place, right? Because we don't have the memory hierarchy, then we have to make it bigger. order to actually feasibly store a real program. So, and that's right on the processor, so that's why it would be bigger.
It's like prime real estate essentially.
Yeah. It's less of an issue now. It was more prime real estate. Like, I can actually show you. So here's a example of a computing system, right? This would be an embedded device, but also more towards consumer post PC era device, right? You have the touchscreen and you have this battery, so we need to be efficient. So we have a more efficient processor, things like this. And your capacity is pretty low for the time, but if you pay double the price, you can get a little bit more capacity. And inside you have your computing board, and on that board is the A12 Bionic, which implements ARM. Right? And this is what I want to show you. So you're mentioning that it's like prime real estate. So you can actually see how much CPU die area is dedicated to memory and actual compute. So NPU, this is a accelerator. This was used for your detection of a Siri. This whole block, that's the size of 2 CPU cores, was just used for that. And then you can see L2 cache is the size of this big CPU blocks, right? And then the small CPU blocks, they share this other L2. Again, it's about the same size. And that's also taken into account. That L1 cache is part of this CPU core. L1 cache is part of this CPU core. And then you have L3 for more cache, right? So now my data is bigger than my processing in terms of general purpose compute. And then you have GPUs 0 through 3. So you have 4 GPUs. This is also compute, but it's not general purpose in the sense of CPUs, right? It's just for graphics, mostly. There's been research the past 10 years using GPUs for general compute. And then all of this other die area is for interfacing with memory. So lots of it is used for memory. Okay? And it's because we can fit a lot more transistors on the chips nowadays. But this was very much prime real estate and mostly data path on the CPU 20 years ago. Okay. Right. So how much time? Yeah, 5 minutes. So this is your transistor. How we're increasing capacity. So it's Moore's law, doubling the number of transistors that we can fit on a chip every 18 to 24 months. And here's your capacity of those. And this is just in DRAM. So you can see it again is very steep growth, but this has died down because we're getting to the size of transistors where quantum compute, like quantum mechanics are making it not behave the way that we want it to, because we're getting to the size of atoms. So this is no longer true. So that's why I mentioned before, my research is on non-traditional computing. Right, so the next chapter, we're just going to get a preview to it. And you'll read about this before Friday, or you have already read about it. So performance, why do we care about performance? We want to know and be informed about purchasing our computers, right? And if you're purchasing thousands of computers, like say your IT at the university, you want to make sure that you're purchasing the right computer. You don't want to waste millions of dollars. So we also want to be able to evaluate those different computers, right? Evaluate it with different applications. We also want to be able to write competitive software. If we do not have the hardware to test our new programs on, then we don't know how it's going to perform, really, right? So we need to be able to write competitive software. And we also, as computer architects, when we're implementing an instruction set, need to know how to increase performance. And then if we're designing a completely new architecture, we definitely need to keep performance up. Okay. So what is performance? We'll talk about that. What are the different performance metrics is what we'll touch on today. And then how to evaluate performance is later on. All right, so what is performance? So here are two examples. This is also going to be in your reading. So the Concorde, I believe this is actually a retired plane. They don't fly them anymore. Or if they do fly them, there's like tens of them. So it has a capacity of 146 passengers, and its cruising speed is 1,300 miles per hour. And then passenger capacity of a much larger plane is 470. So a lot more passenger capacity, but it's half the cruising speed, right? But more than half the capacity. So what we want to highlight here is if we only have one passenger to transport, which one is the obvious choice? Concorde, right? If we have 470 passengers or 400 passengers, which one makes more sense? Right. So the main difference here is in response time versus throughput. So response time is just how long does it take to do the task. But throughput is how many number of things did you do in that amount of time. Right? So we are going to distinguish those two things in the course. So based on those two things of performance, we're going to use those as our performance measures in terms of time. So we have response time and throughput. We're going to focus on this execution time. So execution time is simply the response time. How long it takes to execute the program. And this is going to count everything, including the OS overhead and all of that. And this is a useful number, but it's not good for comparison purposes because you have all of these other variables that affect that time. So what we actually want to pay attention to is CPU time. So this is strictly the amount of time that task spends in the data path on the CPU. So it doesn't count I/O, and it doesn't count swapping, so time sharing on the CPU. And it's going to just be the amount of time on the CPU. So we have remove all those other variables. How fast is this running on when it's actually running? So this is what we more care about. What we're going to focus on. Okay, so just as a reminder, you have a reading and a reading quiz.